I think the first thing to bring up with section 15.4 is just switching into polar coordinates. Since polar coordinates really dominate this section, and I think reflexively, and I think this is true for everybody, when there's a graph, naturally you kind of think of it in rectangular coordinates because the vast majority of the time that's what you end up using. So the first thing that I figured was worth mentioning was how you can switch between them. So x is equal to r cosine theta, y is equal to r sine theta, where r essentially is a radius, and then theta is the angle between, I guess, whatever your cutoff is and the positive x-axis. Right, so just to kind of play with this for a second, like positive x-axis is an angle 0, positive y-axis is an angle pi over 2, right? Because it's a right angle with the positive x-axis. Then negative x-axis is an angle pi, right? Because that's right. There's the pi going from there to there, right? 180 degrees, pi radians. And then negative y-axis is 3 pi over 2. And if you go all the way around, then you're at 2 pi. All right, so then the other thing is, how do you get r from knowing what x and y are? Well, if this is what x and y are, the r cosine theta and r sine theta respectively, then x squared plus y squared is going to be r squared cosine squared theta plus r squared sine squared theta. If you factor out the r squared, and cosine squared plus sine squared is 1, you end up with r squared. So that's probably the easiest way to think about it when you're switching back and forth. And if there's a scenario where you have an advantage with polar coordinates, it's where you don't have things that are angular and where you have regions that look like circles. Basically, that's where it really helps. If you have something that's angular, I think you're better off with rectangular coordinates, but these are not angular down here, and most of what we're going to have in this section, that's kind of what it looks like. So polar rectangles. So first of all, I guess as a comparison to just regular old rectangles, like in a Cartesian plane, where you think, well, what would a rectangle be? Something like -1 less than or equal to x less than or equal to 4, and 0 less than or equal to y less than or equal to 2. Right? So you just have those bounds on x and y that are numeric, and you get a rectangular shape. Well, what if you do the same thing with r and theta? Well, if you do that, then that's giving you 2 bounds on the radius and then 2 bounds on the angle. So these things are actually polar rectangles. Even though certainly that one that's on the left you would not conventionally think of as a rectangle, that's one in polar coordinates, because if you think of the origin as being x squared plus y squared equals 0, which is a long-winded way of naming the origin, but that's correct, right? The only point that would satisfy x squared plus y squared equals 0 be when x is 0 and y is 0, so sure. The radius goes from 0 out to 1 here. So that's what I've got down here, 0 less than or equal to r less than or equal to 1. And this is going all the way around, right? So it's like you start here, and then you go all the way around, you end up back in the same place. Then theta, the angle, is going from 0 to 2 pi, right? So 0 when you start, and when you get all the way around, that's the 2 pi. Then the one that's on the right, that's in between 2 circles. So you have this inner circle that's the unit circle, and you have the outer circle that's got the radius of 2. So then the radius here is going from 1 to 2 out there, and then the angle, well, it doesn't go all the way around this time, it only goes halfway around. So you start at 0, you go halfway, that's pi, so theta is going from 0 to pi. And the best way to think of the limits of integration for r is just to kind of work inside out. So whatever the inside boundary is, that's going to end up being your lower limit. Whatever the outside boundary is, that's going to be your upper limit. So it's inside outside instead of bottom top, or I guess instead of left right, depending on which of the variables you'd be talking about in rectangular coordinates. But that's probably going to end up being the best way of thinking about it. All right, going down here, how to switch from rectangular or Cartesian coordinates to polar coordinates. Okay, well, if you've got a polar rectangle, so like those things up above, where you just have numerical bounds on r and theta, and also that the difference between those 2 bounds on theta is somewhere between 0 and 2 pi, Otherwise, if that doesn't happen, you have to get a little bit creative. It's still doable, but for starting off, that would be a weird thing to do. So we'll just make sure that we keep them in there. Then you end up with this. And you look at it and you go, all right, fine. I see the limits of integration for r. I see the limits of integration for theta, right? The alpha and the beta there. And then for the function, it looks like you just sub in, because we said that x was r cosine theta. There's the r cosine theta. Then y is going to be r sine theta. And then, okay, dr, d theta, but what's that? Why is there an r there? Well, there's a justification of that in our book, and they do a really good job with it. I couldn't do it any better. There's a proof of why you need the r. But the biggest thing for what we're going to do is just not to forget the r, which is really, really easy to do. So that's why I put that in red right there. Don't forget that r. It's so easy to forget that r. If I ever am trying to work out a homework problem and I end up with something that's not what's in the back of the book, that's the first thing I check. Like, okay, did I forget to stick the r in there when I integrated polar coordinates? So yeah, just be careful with that, I guess. Then there's a more general version here, which is rather than just having numerical bounds on r and then numerical bounds on theta, this happens a lot where you end up with the bounds on r being functions of theta, where then it's not nice perfect circle shapes, it's something else. Something curved, but something else, right? So that's why here the bounds on r are g1 of theta and g2 of theta, right? Because that's like right up here where the big R, like the region, is being defined. Then it's like, okay, we got numerical bounds on theta, and I guess that should be a beta right there, not a b. I just caught that just now. So that should really be a lowercase beta, right? It should be that symbol. So I kind of messed that up. But then we've got bounds on r that are functions of theta. And if you're going to have one that's a function of the other, then that's probably the way that it's going to go. It's probably going to be that r is a function of theta and not the other way around. And that's why, if I scroll down a little bit, our book always integrates with respect to r first. Every single example, I think there are 6 in this section, with every single one our book integrates with respect to r, then integrates with respect to theta. You could integrate with respect to theta first in a lot of cases, but if r is bounded by functions, they're probably going to be functions of theta, not functions of r. So then that would mean that your bounds on r are going to be in terms of theta. So then you want to integrate with respect to r first and then theta at the end. So basically our book is playing it safe, but if you play it safe, it'll always work. So nothing wrong with playing it safe there, but admittedly there are cases where you don't actually have to. First example, we're going to integrate this function over r, where r is the region in the upper half plane bounded by the circles with radius 1, radius 2. Okay, usually my first piece of advice when you start with these would be draw the region that you're going to integrate over. It looks hypocritical because I didn't do it here, but it's actually on the first page. Because between those two circles, if I scroll up, it's this right here. It's this one on the right. So you go, okay, we can see what that is. So we know that r has to go from 1 to 2. We know that theta has to go from 0 to pi. So that one already kind of exists. And just for emphasis, I put this in here. In rectangular coordinates, it would be this, right? That x squared plus y squared is between 1 and 4, right? That's basically what this is saying when you say it's in between those two circles. But then that's r. Well, r squared, sorry. Right, r. You could get that r is between 1 and 2 from here, but r squared is between 1 and 4, therefore r is between 1 and 2. And then you gotta have positive y, because it says upper half plane. And the positive y part, or the upper half plane part, if we didn't already have this thing drawn, that's how you get the limits for theta, right? Because if it's gotta stay in the top half, theta's going from 0 to pi. So if you want to write it out formally in set notation, it would look something like that. But we already know what the limits are going to be from the last page, so we can just go right to them. So I'm going to do it dr d theta. So limits of integration for r, 1 to 2, for theta, 0 to pi. And then notice here I just subbed in that x is r cosine theta. And then if y is r sine theta, then y squared is r squared sine squared theta. And then don't forget that r right there, dr d theta. Next step is just distribute the r. That's all I did here. Right, this r right here, just multiplied it through. Then if you integrate with respect to r, this works out really nicely because then the cosine theta and sine squared theta are basically just constants for this part. But you integrate 3r squared, you get r cubed. Integrate 4r cubed, you get r to the fourth. All right, and then double evaluate it at 1 and 2. So then here's that, right? The 8 cosine theta plus 16 sine squared theta, that's what you get when you sub in a 2. And then cosine theta plus sine squared theta is what you get when you sub in a 1. So that's all being subtracted off. Then you can combine like terms a little bit. This move right here, because we know how to integrate cosine theta, that's no problem. Integrating sine squared, it's tough when it looks like that, but there's a formula that you can use, and there are two related ones. They show up frequently in this section. Sine squared theta is 1 minus cosine 2 theta over 2, and cosine squared theta is 1 plus cosine 2 theta over 2. Those get used a lot because it gives you something that's easier to integrate. So here, that seemed like that was the easiest move, at least from my perspective it did. So I said, well, sine squared theta, it's 1 minus cosine 2 theta over 2. I just pulled the over 2 out here, and then distribute the 15 halves, and then all of this is not too difficult to integrate because then it's all right, you integrate cosine to get sine, then 15 over 2, it's 15 halves times theta, and then if you want to integrate cosine 2 theta, that's 1 half sine 2 theta, so I multiplied the 1 half by the 15 halves to get that 15 fourths, and then you just have to double evaluate that. Almost every term is 0 except for, I guess, the second one, right? Because sine of pi, that's 0, sine of 2 pi is also 0, but 15 halves times pi, that's the only term when you do the evaluation that's not going to be 0. So 15 halves pi is the answer here. Next page, the first thing is that a consequence of the general version of polar integration at the end of the first page is how you can get the area of a closed bounded region. It would just be this, right? Where then your r, I mean, maybe you have little r like the radius, maybe that's a function of theta, and so then your limits of integration are going to involve theta. So really this is a consequence of that general version, but I guess you could view it as a consequence of the rectangular version too. But the general version would be a little more proper. So this example that's here, this is actually a little rough. So for the region bounded by the circle centered at the origin with radius 3, x equals 3 and y equals 3, first we want to express the region using polar coordinates. Okay, well, this shaded thing, that's that region, right? Because that circle, it's going to go through 3, 0 and 0, 3. Then we have y equals 3, which is this horizontal line, x equals 3 is this vertical line. So it's this, right? That's what's bounded by those three right there, right? So, okay, well then this looks kind of angular, right? Like if you think about like what the limits of r would be, like the inner limit and then the outer limit, the inner limit's easy, right? Because it's just that circle. You know, okay, well here r is equal to 3, right? Yeah, sure. But when you have something angular, that's a little bit different. And especially because you go, well, then what's the outer part here versus here, right? Like this is x equals 3, this is y equals 3. So I just drew in this dotted line, and I said, okay, well, when you're down here below the dotted line, below the dotted diagonal, then the inner boundary is the circle, but the outer boundary is x equals 3. And then when you're up here above the dotted line, then the inner boundary is still the circle again, but then the outer boundary is y equals 3. So we're going to have to kind of go through these piece by piece. So below the dotted diagonal, the inner boundary is the circle, which would be that r is equal to 3, right? Because x squared plus y squared equals 9. That means r squared is 9, so r is 3. And then the outer boundary is x equals 3, but how do you write that in polar coordinates? Well, we said that x was r cosine theta. So basically I just subbed in here and I said, okay, well if x is 3, then r cosine theta is equal to 3. But then that would mean that r is 3 over cosine theta, but 3 divided by cosine theta is the same as 3 times secant theta. And then above the dotted line, you kind of do the same stuff. The inner boundary is still going to be that circle, so we can still say, all right, that's r equals 3. But then the outer boundary is y equals 3, and you do the same sort of thing. And then you say, well, how do you write y in polar coordinates? R sine theta. So then r sine theta equals 3, and then solving for r, you get 3 over sine theta, but dividing by sine is the same thing as multiplying by cosecant, so that's 3 cosecant theta. The other thing that we're going to need, because basically here now we've got the limits for r, right? Because for this part, it's from 3 to 3 secant theta. For this part, it's from 3 to 3 cosecant theta. Now we actually need limits for theta. Okay, well, overall, this is going from 0 to pi over 2, but we're going to have to break this into pieces because what happens here and what happens here are different. So then we just have to figure out the angle where we have to switch from lower part to upper part. It's what you would think. I mean, I think just kind of looking at this, you'd go, it's got to be pi over 4, right? Like this is a square and we're breaking it on the diagonal, and sure. But just to make it a little bit more formal, if this is theta right here, so just the angle between the x-axis and the dotted line, then the tangent would be 3 over 3 because you have 3 for the opposite and then 3 for the adjacent. So the tangent's going to be 1. So if the tangent is 1, theta does have to be pi over 4. Okay, so then here are our limits of integration. So below the dotted diagonal, so that's going from where theta is 0 to where theta is pi over 4, then we've got limits of integration for r of 3 and 3 secant theta. If you go above the dotted diagonal, you're starting at pi over 4, and then you're going up to the positive y-axis, so that's pi over 2. And then the limits of integration for r, 3 and 3 cosecant theta, like they are right up here. Okay. So then in polar coordinates, if you wanted to write it in set notation, basically it's just the union of these two things. So on the left, that set is just the below the dotted diagonal, right, where I've got theta between 0 and pi over 4, and then r between 3 and 3 secant theta. And then this one over here is above the dotted diagonal. And you can tell just from the theta bounds, right? Pi over 4 and pi over 2. So okay, well, that's expressing the region using polar coordinates. I said this one would be a little bit rough, and it ends up that way because you have to break it into 2 parts. Because if I scroll back up for a second, that's a little too far. There we go. That what's on the outside of that shaded region is not always the same thing, right? Sometimes it's x equals 3, sometimes it's y equals 3. And that's the way that you've got to handle it. And I wanted to have one where that happened because it's not like that's a thing that never comes up. It does happen every once in a while. Also with this example, I wanted it to be one where we could easily check to make sure that we had the correct area. And this is one where you don't actually have to do the integration to get the area. Because if I scroll back up to where the picture is, this is a square, right? It's a square where each side is 3. And then this unshaded portion of it is 1/4 of a circle of radius 3. We know how to get the area of a circle, right? Pi r squared. So that's basically what I did down here, where I said, well, it's the area of a 3 by 3 square minus 1/4 the area of a circle with a radius of 3. So square area minus 1/4 circle area, you get 9 minus 9/4 pi. And this is one where, you know, if you get one that looks like this, where you can use like those old geometric area formulas to get it, then do it that way. It'll be a lot faster. But I did want to have one where we did it both ways, where it was easy to check. So the area with integration is much, much longer. So you've got to break it up into 2 pieces, right? So there's the under the diagonal. This one is above the diagonal. The integration, I guess, is about the same, right? Because you're just integrating r. So 1/2 r squared, there's 1/2 r squared. Different limits of integration, though. So when you square 3 secant theta, you're going to get 9 secant squared theta. So secant squared is an easy thing to integrate. So is cosecant squared. And then that's what happens, right? Because then we get down here, and what we're going to end up with is that we've got, well, when you integrate secant squared, you get tangent. When you integrate cosecant squared, you get the negation of cotangent. So it looks like that's working out pretty well. And then, let's see, going down a little bit farther. This thing is huge because I put every single term in there. All right, so those first two terms are for subbing pi over 4 into there, then subbing 0, then going over here, subbing in pi over 2, and then subbing in pi over 4. So what you end up with, so 9 minus 9/4 pi, then you get some zeros, right? That's a 0, that's a 0, that's a 0. Then minus 9/2 pi, then that's a 9, right? Since if tangent of pi over 4 is 1, so it's cotangent of pi over 4. And then 9/4 pi. So let's see, that and that are going to add out. So it looks like we should have 1/2 times 18 minus 9/2 pi. Then you distribute the 1/2. And you get 9 minus 9/4 pi, just like we got before. So yes, this is much longer, but you don't always end up with something that's that nice geometrically to begin with, right? You don't always have a circle inside of a square. So a lot of times you do have to grind all this integration out, but really it's not too bad, right? I mean, parts of it look long, but the integration itself was not really that bad. And that tends to kind of be how these go. I guess every once in a while, maybe you have to do a U substitution or like, something like that. But usually the integration itself is not anything too crazy. For example 3, we want to find the area in one leaf of this 4-leaf rose. And I suppose just knowing that it's a 4-leaf rose is probably enough to draw this thing, and knowing that r is cosine 2 theta, because then you go, all right, well then when theta is 0, then we're going to get that r is 1, and so then from there, you know that that's got to be the farthest point out of that leaf, and that probably gives you enough to draw this entire thing, right? But the important thing as far as the angle goes is where do we have to cut this off? And so that's what this part is. So if r is cosine 2 theta, then when do you get 0 for r? Well, it would be whenever this cosine works out to be 0. So you think, well, when is cosine usually 0? Pi over 2, negative pi over 2, right? But then since it's cosine 2 theta, if theta is pi over 4, then you're taking the cosine of pi over 2, you're going to get 0. And then if theta is negative pi over 4, then that's going to be the cosine of negative pi over 2, and that's going to be 0. So those are our limits of integration for theta. And then, right, which is right down there again. And then for r, it's starting at the origin and then going out to cosine 2 theta to get that leaf shape. So here we go with the area. Then there are limits of integration for theta. There are limits of integration for r. And then the integration is about the same as the last one, just, I guess, with different limits. And that it's only one double integral instead of two. So you integrate r, you get 1/2 r squared, double evaluated at 0 and cosine 2 theta. So I brought the 1/2 out front, and then I said, well, it's going to be cosine squared 2 theta. And then notice again, I end up rewriting. Because with that cosine squared, that's kind of a tough thing to integrate. So that would be 1 plus cosine 4 theta, right? 'Cause 2 theta times 2 over 2. So I just brought the 1/2 out in front and then brought it all the way out here. Because then integrating this is not so bad, right? You integrate 1, you get theta. You integrate cosine 4 theta, that's going to be 1/4 sine 4 theta. And then double evaluating that. So pi over 4 plus 1/4 sine pi, but that's a 0. And then minus negative pi over 4 plus 1/4 sine negative pi, that's also a 0. So inside the brackets, ultimately it's pi over 4 plus pi over 4, which is pi over 2. Multiply that by 1/4, and you get pi over 8. And so that's the area inside one leaf. So I guess if you wanted the area of the whole thing, it's pi over 2. But yeah, for the one leaf, it's just going to be pi over 8. Example number 4. I added in some extra stuff in this one, which makes it really long. That's why it has an extra page. But I wanted to show what happened if you tried to just like bulldoze through it using rectangular coordinates. You end up in trouble, which makes sense because if you look at these limits of integration for x, you go, that looks like a circle, right? Just solved for x. And when you have something that's circular, you're usually way better off with polar coordinates. But if you tried to do it, so here I said, okay, I'm going to integrate with respect to x. So then I'm going to have to double evaluate this thing. But then that's going to be 4 minus y squared raised to the power of 3 halves. And then minus a minus will be a plus, so we get another one of those. And so then since there are going to be 2 of this term, I factored out that 2. But then you end up having to integrate this, and that's trouble, right? You look at that and you go, well, u substitution's not going to work. And you go, well, then, like, is a trig substitution going to work if then you used like one of those double angle formulas? And, like you start kind of going through things and you go, I don't know about this, I don't know about this. So the integration ends up being kind of rough if you go that way. However, if you switch to polar coordinates, so here, the limits of integration for x were these two, right? The square root of 4 minus y squared and the negation of that square root. Either way, if you square both sides, you get this, that x squared is 4 minus y squared, but that's x squared plus y squared equals 4. And you say, oh, well, then that's a circle of radius 2. But going back up here for a second, the limits of integration for y are 0 to 2. So if y is only going from 0 to 2, then that means it's just the top half. So that's what we've got here. So yeah, it's that circle with radius 2 centered at the origin, but it's only the top half of it. So it's the upper half circle. So r is between 0 and 2, and then theta is between 0 and pi, right? Just going halfway around. And then that's a thing that we can integrate. So the function was x squared y squared. So there's my x, right? Because x is our cosine theta, so I subbed that in for x. And then y is our sine theta. You square those, you end up here. I kind of cleaned this up a little bit and said, okay, ultimately you've got an r to the 5th in there. Cosine squared theta, sine squared theta. And then go into the next page. All right, well, if you integrate with respect to r, then the cosine squared, sine squared is basically just a constant at this point. But then you integrate r to the 5th, you get 1/6 r to the 6th. Double evaluate that at 0 and 2. The 0 is not going to give you anything, but the 2 will, right? 2 to the 6th is 64. So you got that 64 over 6 in there, which I then pulled out front. And then I rewrote both of these using those formulas. So there are those formulas again, right? That cosine squared is 1 plus cosine 2 theta over 2, and sine squared is 1 minus cosine 2 theta over 2. So I've used those, pulled that 1/2 and that 1/2 out front to get the 64 over 24. Then you end up, I guess, multiplying those together, you're going to get the difference of squares. So 1 minus cosine squared 2 theta. And you go, all right, well then you could rewrite that as sine squared 2 theta. And I also reduced that fraction out front. The sine squared 2 theta, you can rewrite that as 1 minus the cosine of 2 times 2 theta, which would be 4 theta all over 2. And then brought that 1/2 out front to get the 4/3. Then this is pretty easy to integrate. You'd end up with theta minus 1/4 sine 4 theta, evaluated at 0, and pi. The 0, again, is just going to give you a bunch of zeros. When you sub in for pi, you're going to get pi minus 1/4 sine 4 pi. This term's also a 0. So really the only thing in the brackets is the pi, and you end up with an answer of 4/3 pi. The last example, it looks like it's going to be more difficult because of the way it's phrased, yet it's actually way shorter than example number 4. So I guess those are sort of counterintuitive thoughts, but that's the way it works out, because here it's just phrased as getting the volume of the solid above the xy plane. So that is just going to be a double integral. And basically it means that you're just going to figure out the region of integration and then integrate that function right there, right? The paraboloid one. And there is a picture of this, which is stuck in with the notes that go along with this section. I made one in GeoGebra if you want to take a look at what it looks like. But you could do it algebraically too, because you could say, well, then where do these things intersect? Well, if z is 0, you get 0 equals 1 minus x squared minus y squared, or x squared plus y squared equals 1. So the paraboloid is going to intersect the plane in that circle. And this is a paraboloid that opens down. Basically, it's like there's a hump that's over that circle, right? It's what you would normally think of as being the shape toward the bottom if it was one that opened upward. Right now, it's like the hump on top. So the solid that we're trying to get the volume of, it's under the paraboloid and above that disk, right? Because it's going to be above the xy plane, but we know that the paraboloid is going to intersect the plane in that boundary. So really we just got to worry about being above this disk, right? This filled in circle. So in polar coordinates, this one is not too bad, right? You go, well, this is a unit circle, so that means r has to go from 0 to 1, right? So origin out to there, out to the boundary, and then we're going all the way around the circle, so theta is going from 0 to 2 pi. So this volume is not so bad because the thing that we're supposed to be getting the volume of, right, it's underneath that function, right, because that's the function for the paraboloid. But x squared plus y squared is r squared, so I just subbed that in directly right here. And then you can distribute the r, so r minus r cubed, and then integrate with respect to r, you end up here. Double evaluating that, you're just going to end up with 1/4, right? You're going to get 1/2 minus 1/4, and then minus 0. So, all right, 1/4 d theta, integrating from 0 to 2 pi. Well, that's just 1/4 theta evaluated at 0 and 2 pi, ultimately pi over 2. So that one actually ended up being really short. And I just wanted to have one in here that had that other phrasing, and it felt like that one belonged at the end, even though it does feel a little weird that the last problem is maybe half as long as the one before it.